This instrument is called a harpsichord. The man tuning it is Dr. Eiichi Nakamura. He is an organic chemist.
昔の話をするとアインシュタインはなんかバイオリン弾いたっていう話ですよね。我々の友達見ても科学者に限らずサイエンスやってる人はね結構音楽やりますよ。
Chemistry and music. You might feel that these two fields have nothing in common. Dr. Nakamura enjoys both. Let's see what kind of research he does. This is a piece by Handel, a famous composer of Baroque music. Baroque music flourished in Europe from the 17th century to the middle of the 18th century. You might call it the parent of classical music.
実は音楽は和音にベースしてるんで、科学はもちろん科学的原理にベースしてるわけですね。そういう意味では同じですよね。音楽もそのサイエンスもね科学もですね、これやっぱり自分の意見を外に表明する、それから自分が感動したことを人に伝えるという点でね、実は同じなんです。
The Nakamura Functional Carbon Cluster Project. This is Dr. Nakamura's research base. In this space dominated by white, oranges and blues stand out. The laboratory consists of orderly rows of experimental equipment. There is a simple beauty in Dr. Nakamura's laboratory. Safety is a big concern here. There is a fume hood which produces ventilation so that researchers do not come into contact with chemical fumes. A sensor detects whether someone is present, which automatically adjusts the ventilation. All of the fume hoods work together to expel air in an efficient manner. Filters remove toxic matter before returning the air outside. These are the device fabrication instruments, which are used to process synthesized chemical compounds. They are connected in sequence to facilitate skillful handling and to prevent the compounds from being exposed to the air and moisture. They are like a small device production line. A beautiful, functional laboratory. It is here that Dr. Nakamura pursues his research using carbon. The Nakamura Functional Carbon Cluster Project. First, let's review what carbon is all about. This is a carbon atom. Carbon atoms can bond with each other to produce various types of molecules. Molecules whose skeleton consists of carbon atoms are called organic molecules. We human beings are an assembly of organic molecules. An organic molecule featuring a hexagonal arrangement of carbon atoms is called benzene. Benzene can bond with other molecules to form a variety of compounds. One example is penicillin. Benzene can be used in useful drugs that protect our health. Then there are fullerene and carbon nanotube. A large number of carbon atoms come together to form beautiful compounds. Such an assembly of carbon atoms is called a carbon cluster. What could carbon clusters be used to make?
フラーレンっていうのはここにこうあるこの黒い粉ですけど、こう見るとで、これがその炭素が60からできた分子なんですね。でこれこのままでは水にも溶けないし有機溶媒にも溶けない。それをその科学の力で例えば水に溶けるようにするというようなことを鍵にして応用に持っていくと、そういう研究を5年間行ってきました。バロック音楽ってやっぱり基本的に通奏低音というのがあって、その上に和音を積み重ねて作る。それから和音とあとは対比法ですね。和声音と対比法が非常に絡み合って非常にきれいな形で出ている。これ物理も科学もサイエンスって一般的にそうですけども、原理っていうのがあって、そこに事実がこうなんていうのかな流れていて複雑に絡み合うと。
Are things born of principles the same in chemistry and music? According to Dr. Nakamura, chemical formulas can take on the appearance of a musical score. Let's ask Dr. Nakamura's staff to show us how they compose and play fullerenes.
Material can be used as obstacles so that we may be
Translate and excited state.
The people gathered here are members of Dr. Nakamura's project team. This team has developed a number of new synthetic techniques, creating many molecules that no one has ever synthesized.
デザインしようよね。誰も考えたことないね。そういう研究が面白いでしょ。本当に。
I try to.
Here are some examples of the work done by Dr. Nakamura's project team. On first glance, they have unique forms similar to modern architecture or works of art. On closer look, each molecule has a fullerene in its center, while other molecules, like benzene, bond to the fullerene like an adornment. For example, here is a case where two benzene molecules bond to a fullerene via silicon. It has an amusing shape, reminiscent of a rabbit's face. This is one of the experiments of the project team. In this molecule, 5 benzenes bond to a fullerene. It looks like a small flower or a king's crown. This molecule was the first of many new molecules to be synthesized by the project team. Let's now extend the tip of these 5 benzenes. What does this look like? An octopus? A badminton shuttlecock? In fact, this molecule is named shuttlecock-shaped. When heated, molecules of this type become nested with each other, forming a column-like shape. Individual columns can then come together in a bundle. Let's observe this state with a microscope. This structure is called a liquid crystal. Starting out as a black powder, fullerene can be used to create this beautiful pattern. A structure called cyclophenacene was also created by adding benzenes to fullerene. Take a good look at the middle of this molecule. 10 benzenes connect to each other in a circle. Actually, this structure was theoretically predicted in 1954, but no one had been able to synthesize it until now. A world's first, this cyclophenacene was not achieved by assembling it from scratch, but rather by reducing the fullerene bonds. Irradiating cyclophenacene with ultraviolet rays causes it to emit light of various colors. In this way, coal-black fullerene can be made to emit light. Now, what do 5 arms enclose? It's an iron atom. What does this molecule resemble? None other than the Apollo lunar module. This molecule can be made to land on an electrode, and by irradiating it with light, currents flow through it. Electrons from the iron atom flow along the fullerenes and benzenes. This technique is a good match for fullerene and metal. The project team also created a molecule that encloses 2 metal atoms. This is a double-decker type of metal fullerene. It's about 1 nanometer in size, or 1/1000th of a meter. It's understood that one of these molecules may be able to function as a transistor. In fact, this is really a small transistor made with fullerene and metal. Dr. Nakamura's project team also discovered something else. First, let's represent fullerene as a green sphere and benzene as a yellow rod. Let's place many of these molecules in water. Fullerene, like oil, does not mix well with water. So the molecules come together and spontaneously form a film. The film curls up on itself, forming a large sphere. Such film could be used as a filter to separate substances. A fullerene is an assembly of carbon atoms bonded in the shape of a soccer ball. Many new properties have come to light by combining fullerene with a variety of molecules and atoms. The project team has created many variations of fullerene through firm theory and synthesizing techniques underpinned with a great love of chemistry. What kind of molecules will his staff create next? No doubt they will continue to compose and play fullerene variations without limit. A team member is carrying some synthesized carbon clusters. Where is he going? To the device fabrication instruments that we saw before. A device is a small apparatus that has a certain function. What kinds of devices can be made from carbon clusters?
今お話に出てきたようなフラーレンを化学修飾してで溶けるようにしましたと、こうなりましたけど、今度隣の部屋でこの太陽電池を作ってます。で私たちは世界最高レベルの、その炭素クラスターの 化学主食技術っていうのかな、そういう科学を持っていたので、我々がこの太陽電池の分野に参入すれば世界の誰にもできないような新しい太陽電池、高効率の太陽電池ができるという、信じてたんです。もう信じたとしか言いようがないですね。何の証明がないですから。
Here is a cross-section of a solar cell where N layer, I layer, and P layer are stacked between a cathode and an anode. Irradiating the I layer with light generates electrons and holes. The electrons move toward the cathode while the holes move toward the anode. A solar cell produces current in this way. An organic light-emitting diode, or OLED, has a similar structure. The phenomenon that occurs here, however, is just the opposite of a solar cell. Electrons and holes recombine with each other in the emission layer, giving off light. In either a solar cell or OLED, the main issue is to create materials that can generate and conduct many electrons and holes. The project team has taken up this challenge using carbon clusters. Let's see how a solar cell is fabricated. First, synthesized molecules for the P layer and I layer are dissolved in a solvent, which is then thinly applied on a substrate. The resulting substrate is then heated to 180 degrees. The coating then changes from purple to green. This is the molecular structure when the coating is purple. On applying heat, the molecule changes into one, having 4 benzenes arranged in the shape of a cross, and the color changes to green. This transformation enables the molecule, which cannot be dissolved in a solvent, to be coated onto a substrate. Next, synthesized molecules for the I layer and N layer are applied on this coating. The molecular structure has the shape of a rabbit's face, which we saw earlier. The substrate is now placed inside vacuum evaporation instruments. After removing the air, it deposits metal atoms on the substrate. This forms the cathode. Finally, the substrate is packaged with no exposure to air or moisture, and the solar cell is completed. The organic thin-film photovoltaic cells are cheaper than today's silicon solar cells in material and fabrication costs. What counts most, however, is performance. Let's measure the amount of current generated by light irradiating these cells to determine its efficiency. Conversion efficiency is about 5.5%. This is about 3 times the performance from a few years back. However, a silicon solar cell has reached a 10% performance level. Dr. Nakamura's project team is aiming for higher efficiency. New molecules were also synthesized for the OLED, enabling the achievement of higher performance.
でも実際上最初2年間およそ全くデータが出ませんでしたけども、この3年ぐらい前から少しずつ 1%、2%、4% で今年の5月に 5% も超えて、我々なんとか 6%、7% に今年行くんじゃないかと思ってます。シリコン太陽電池の問題点は実は作るのにエネルギーがすごくかかる。そもそもエネルギーがこんなにかかるのにこんだけしかエネルギーが戻ってこない。それに対して私たちがやっている有機薄膜太陽電池っていうのは実はエネルギーを使うエネルギーはシリコンの10分の1ぐらいしかかかる。これくらいのエネルギーでこれくらいできるんですね。そうなると全体のエネルギー効率からいうと実は有機薄膜体電池はものすごくいい ということになります。
Combining Dr. Nakamura's research style of molecular design and synthesis based on theory, together with carbon clusters, could lead to important changes in our society in the near future. This is the National Institute of Advanced Industrial Science and Technology, or IST. Here, we can find a high-resolution transmission electron microscope which was designed by Dr. Kazutomo Suenaga, group leader during the initial phase of the project. In 2007, this microscope was used to achieve a world's first by successfully observing a certain something. This certain something was an organic molecule. The microscope was able to capture the form of one organic molecule. It was Dr. Nakamura's project team that also developed this electron microscope.
私は有機化学者ですから長年こういう有機分子を作ってそして構造を決めてその機能を調べるっていうのをやってきました。でこのプロジェクトをやるにあたって待てよとこれなんか自分で物を作ってるような気にはなってるが実は見たことがない。金属原子が一個一個こうそこにあるとかですね、金属原子が動く様子っていうのはもうずいぶん昔から電子顕微鏡で見られていたんですけども有機分子を見た人はいなかったと。で正確に言うと一つの有機分子を見た人はいなかった。でそれは有機分子っていうのは炭素と炭素がこう結合してくっついてるわけですね。でその結合している様子を見たいと思った。
We have been representing organic molecules using CG and molecular models. But do real organic molecules have the same shapes? The best way to answer this question is to actually observe organic molecules. However, at room temperature, organic molecules move at a speed that electron microscopy cannot capture. For this reason, organic molecules are made into a crystal, suspending movement and enabling them to be captured by an electron microscope. However, this technique still can't capture the image of a single molecule. Furthermore, shining an electron beam may dislodge or even destroy organic molecules. How can the movement of organic molecules be stopped without destroying them? Dr. Nakamura's project team had an idea using carbon clusters. The first step is to synthesize organic molecules designed with obvious shapes. Here is one example, in which a long organic molecule is attached to boron atoms. These types of molecules are put in a glass tube together with carbon nanotubes, and the air inside the glass tube is removed to form a vacuum. The glass tube is then heated to over 100 degrees centigrade. This heating causes the organic molecules to spontaneously move inside the carbon nanotubes. This carbon nanotube containing organic molecules is then set inside an electron microscope. This electron microscope is able to cool the sample to minus 269 degrees centigrade and irradiate the molecules with electron beams. These beams that are scattered by the organic molecules make an image on the screen, or a silhouette of that organic molecule. What do we see here? This tube-like structure is a carbon nanotube. and the thing moving inside it is an organic molecule. This microscope can also determine element type. This black shadow corresponds to boron, which was used here as a marker for locating organic molecules. Here, we see a two-legged organic molecule that is revolving. Its orientation and shape are constantly changing. Here, an organic molecule appears to be escaping through a hole in the carbon nanotube. This organic molecule seems to be moving just like a living thing. And so, a molecule has been created through design. It was confined in a carbon nanotube and observed by electron microscopy. These three techniques made it possible to observe actual organic molecules. Human beings are an assembly of organic molecules. We are finally able to observe organic molecules and gain a deeper understanding of them. This is certainly a significant moment for us. Baroque music evolved into classical music, and classical music grew into the various types of music we hear today. Even as the times change, the musical theory of Baroque music lives on.
まあ、私の研究分野って理論科学もやってるし有機合成もやってて、それから太陽電池もやってますし、それから電子顕微鏡もやってる。だけどこれを通して一つある思いっていうのは、とにかく今まで誰もやったことないことをやりたい。でそしてその誰もやったことないことをやっぱり完璧にやりたいですね。で完璧にやるためには基礎がないとできないですよね。僕たちが持っている有機化学の基礎があって、その下に物理もあって、そういうものを全部使ってなるべく高く飛んでいこう、上に飛んでいくんだ、そして狙えるものは全て撃ち落とすと、こういうふうに研究やっていきたいと思ってます。
Whether considering music or chemistry, the importance of the basic foundations will never die out even as time progresses. Likewise, the relationship between human beings and molecules is permanent throughout time. Dr. Nakamura's research highlights the importance of thinking about things based on the fundamentals that will never die out.